Isomerism, organic compounds that have the same molecular formula but different molecular structure. We've already learned on structural isomerism that have different in connectivity. Now we're going to learn stereoisomerism. Same connectivity but different arrangement in space. Stereoisomerism, chemical compounds which have their atoms connected in the same order but different in the arrangement in space. There are two types of stereoisomerism: optical isomerism or enantiomer. The second one, cis-trans isomerism, distereoisomer. Optical isomerism involves carbon that has chirality center. The molecule and its mirror image are non-superimposable. Compounds are able to rotate the plane polarized light. That's for optical isomerism. In cis-trans isomerism, the molecules are not mirror image, non-superimposable of each other. So these are the different. Cis-trans isomerism, not mirror image. Optical isomerism, mirror image. The isomer of it is mirror image. But both are non-superimposable of each other. Cis-trans isomerism, free rotation is prevented by the presence of C double bond C, carbon-carbon double bond, or the free rotation is prevented by cyclic structure. So there's no free rotation in cis-trans isomerism. Enantiomer. The molecule, enantiomer, the optical isomerism, enantiomer, the molecule and its mirror image are non-superimposable, occur only with compounds whose molecules are chiral. That's enantiomer, optical isomerism, molecules that are chiral. Chiral molecule means a molecule which has a carbon atom attached to 4 different atoms or groups of atoms. For example, this is carbon, 4 different atoms: bromine, chlorine, hydrogen, fluorine. 4 different atoms. No 2 atoms are the same. That's chiral molecule. All 4 must be different. And this is one molecule, and the isomer of this molecule is mirror image of it. This is mirror image. So it's like you put a plain mirror in the middle and you have another mirror image here. So mirror images are non-superimposable chiral molecules. So we can say that compound A and B are a pair of enantiomers. They are optical isomerism or enantiomers. Why? Because they have chiral carbon. This carbon, we call it chiral carbon because this carbon attached to 4 different atoms or groups of atoms. In this case, 4 different atoms. It can be groups of atoms as well. This is the 3D representation for chiral molecule. We use the wedge line, means bond in front, so means the bond come up from the paper. Wedge dash, the bond behind, means the bond goes into the paper. The solid line, bond lies in the plane. So these two are solid lines, bond lies in the plane, and for this atom with wedge line, bond in front come out from the paper. This wedge dash, bond behind, means it goes into the paper. This is a mirror image of compound A. So these two are optical isomers or enantiomers because this carbon has 4 different atoms or group of atoms. Optical activity. I've mentioned optical isomer before, which are enantiomers. Now we'll look at what does it mean by optical activity. It is the ability of a chiral compound to rotate the plane polarized light. So if it is optically active, it can rotate the plane polarized light. Chiral compound rotates the plane polarized light. So means chiral compound is able to rotate the plane polarized light. Thus, chiral molecule is optically active. Isomer, which rotates the plane of polarization to the right, means clockwise, is dextrorotary isomer. We use D or plus symbol isomer to represent dextrorotary. The isomer, which rotates the plane polarization to the left or anti-clockwise, is levorotatory isomer. L or negative symbol isomer. If you see L symbol or negative symbol isomer, the isomer rotates the plane polarization to the left. It means it rotates anti-clockwise. So this is the plane of polarized light has been rotated. We have light source and polarizer. This is the polarizer. Plane of polarized is changed. This is the chiral compound sample tube. In the sample tube, we have chiral compound. The analyzer can see that the plane of polarized light has been rotated. These two, 1, 2. This one from the polarizer. Second one, near the analyzer, the plane of polarization is changed. Why? Because in the sample tube, there is chiral compound. But if in your sample tube, a chiral compound means this compound has no chiral carbon. Achiral means non-chiral. So when there is no chiral compound or chiral carbon in the compound, the plane of polarization is not changed. It remains the same because no chiral carbon. If there are chiral carbons, the plane of polarized light has been rotated. But if there's no chiral carbon, the plane of polarized light has not been rotated. For example, we have the molecule of lactic acid, the carbon attached to carboxyl group, attached to one hydrogen, attached to one methyl group, attached to hydroxyl group. There are 4 different groups of atom. If there are 4 different groups of atom, we can say that this carbon is chiral carbon. This is chiral carbon. We use this like star symbol. We call it asterisk. Okay, because they have this carbon attached to different groups of atom. Asterisk. So this is chiral carbon. The molecule is chiral molecule. So if it's chiral molecule, it is optically active. Why optically active? Because chiral molecule is able to rotate the polarized light. This one, L, lactic acid, anti-clockwise rotation, anti-clockwise. This one, clockwise rotation. So make sure if you draw the enantiomers, make sure it's like you're drawing side by side, and in the middle, imagine that's a mirror plane in the middle, and that's how you draw enantiomers. So those two are a pair of optical isomers. Next, the second type of stereoisomerism. The first one is optical isomerism, the molecule that is able to rotate the polarized light. There are mirror image, non-superimposable. Now, cis-trans isomerism or distereoisomer, The molecules are not mirror images and non-superimposable of each other. Different from optical isomerism. Optical isomerism, mirror image. Cis-trans isomerism, not mirror images. There are two different atoms or group of atoms on each doubly bonded carbon atom. This is the requirement for you to say it is cis-trans isomers. It must have two different atoms or groups of atoms on each doubly bonded carbon atom, or in the cyclic structure, the carbon in the cyclic structure, because it involves C double bond C or cyclic structure. So the carbon itself must have two different atoms or group of atoms. For example, this one. This carbon, we focus on this carbon. It has two different groups of atoms. This carbon attached to methyl and one more attached to hydrogen. So these two are different. If this carbon has the same attached to the same atom or same groups of atoms, for example, carbon has H and H, same atoms, there will be no cis-trans isomerism. The carbon must have two different atoms or group of atoms. So this carbon, different as well. One methyl, one hydrogen. This carbon, one methyl, one hydrogen. This carbon, one methyl, one hydrogen. So there is cis-trans isomer if there are two different atoms or group of atoms on each carbon. So this carbon, different atom. This carbon, different atom. Same goes to this carbon as well, and this carbon. Two groups. For cis isomer, two atoms or groups of atoms which attach to different carbon on the same side. For cis isomers, two atoms or groups of atoms which attach to different carbon on the same side. So the cis-trans isomer, the requirement for cis-trans, one carbon must be attached to different atom or groups of atom. For cis isomer, because cis-trans is general, so now we divide them into two: cis isomer, trans isomer. For you to say it is cis isomer, two atoms or group of atoms which attach to different carbon on the same side. So there's two different carbon, this in cyclic structure, carbon, single bond carbon, okay, and two different carbon on the same side. So same side, hydrogen, hydrogen on the top part, and methyl, methyl on the bottom part. So this is cis isomer. For this one, carbon double bond carbon, because cis-trans isomer involves cyclic or carbon-carbon double bond. So for carbon-carbon double bond, you have two same atoms, hydrogen, hydrogen, on the same side, and two different groups of atoms on the top part. This one, the top part, CH2, CH3, CH2, CH3, same side, hydrogen, hydrogen, same side. So to identify cis isomer, you have to search for two atoms or two group of atoms which are the same. For this one, hydrogen and hydrogen, same atom on the same side. These two groups of atoms on the same side. These two atoms on the same side. These two atoms on the same side, and two groups of atoms on the same side. Then you can call it cis isomer. For trans isomer, two atoms or groups of atoms attached to different carbon on the opposite side. So for trans isomer, search for same atoms or same group of atoms which attach to different carbon but opposite side. Now you can see same atom, hydrogen and hydrogen. This one top part, this one the bottom part. So trans isomer, because opposite side. Top, bottom. Same atoms. These two, same groups of atom. Ethyl, ethyl. CH2, CH3, CH2, CH3. Two groups of atom, opposite side. The top side, the bottom side. And then, in cyclic structure, same atom, hydrogen, hydrogen, one on the top side, one on the bottom side. Methyl group, one on the top side, one on the bottom side. And for this one, same atom, hydrogen, hydrogen, top side, bottom side. And in cis-trans, remember in cis-trans isomerism, the carbon must attach to different atom. This carbon, different atom or group of atom. This carbon, different atoms or group of atoms. Okay, remember that requirement.